Hi, I'm Björn at Qoitech, and today I'm going to show you the 3 best practices to get that long battery life for your IoT device. There are 3 steps to consider. First step is know your device. In this step you will optimize design and measure for all conditions. Second step, profile your battery. In this step you will evaluate and pick the right battery for your device, not based on datasheet but actual measurement. Third step is emulate the battery for your application. In the end you will have an estimate of the battery lifetime of your device. I will use the following setup. As IoT device, I have chosen the sensitive strip MSH. It's an ultra slim LoRaWAN device. It has temperature, humidity and light sensors. It also has a magnet sensor, and this is what I will use when I trigger one active event. I also use the OTI Arc from Qoitech. It's a small portable power supply. It measures current consumption as well as voltages. It also has a data acquisition. It can also profile and emulate batteries, and this is why this is so great when we work with this 3-step method. Okay, the first step is to know your device. So let's start by connecting my device. I have the OTI here. I will use it only through USB here. And let's connect that first. So since my device is a 3-volt device, to have USB cable connected is enough for my power. If I need more power, I can connect a DC adapter that's connected on the back side of the OTI. Then I can go up to higher voltages. So let's connect the sensor. So I power it through the main port here. To know more about my device, to be able to optimize it, I can also use more functions, like if I have the possibility to send out UART signals from my sensor, I can connect that to the expansion port. On the expansion port there are other functions that is also very useful when I work with optimizing my design. I can measure a subsystem current, and I can measure more voltages than only the main voltage here. I can also measure some digital signals. So the more information I have, the better I can optimize my design. So let's power up. I go to OTI application. I choose 3 volt, and I have set an overcurrent protection here as well. Okay, so it's being powered up now. I will start by including the sensor to the network. I do this by a magnet here on this side of the sensor. 1, 2, 3. So now the sensor is being included in the LoRa network. Okay, so now it's included. So what I will do is that I will record and measure different activities. So let's say a use case where I have 1 activity per hour and the sensor is far away from the gateway. Then I will set the data rate to 0. That means a spreading factor 12. The other use case I will look at is if I'm closer to the gateway. So I will set the data rate to 5 with a spread, that means spreading factor 7. And then I will have more activities per hour, and I will choose to have 4 activities per hour. So that is more like opening closing sensor. And the first use case with one activity power, maybe it's just a temperature, humidity sensor sending every hour. And I need to wait a little bit after the inclusion in the network before I start to do activities, since I'm limited in how much I am allowed to send in the LoRa network. So first, now I will set the data rate to 0. And I send the data when I get an activity. So let's have an activity here. I get the magnet sensor. So here is my activity. And actually, during this activity, the message to set the device to data rate 0 was also being received. So let's wait a little bit longer and do a new activity, so we are sure that this setting is being received. Okay, so let's have an activity now. So here is my activity. For example, when some data is being sent, like a door was opened or a temperature was being transmitted. So let's measure this part. We have a high part here, roughly 1.3 seconds, with an average current consumption of 38 milliamp. And if we look, the complete activity, it consumes roughly 44 microwatt hour. We also need to measure the sleep current. And now I want to measure that for a minute, at least for this workshop. If I was going to do this during development, then I would choose to have a much longer period where I measure sleep current. I would also do my measurement for the activities several times to see if I get variations. So here is a sleep period, and I can see that the sleep current consumption is 1.43 microamp, and for 1 minute the energy consumed during sleep is roughly 72 nanowatt hour. And I need to multiply this by 60 to get the correct energy consumption per hour in sleep mode. So now I have both a sleep and an active event. And the sleep is a factor 1000 less than the active event. So when I measure my active event, I can disregard the sleep current consumption. I could subtract that from the measurement, but the difference will be so small. So let's send new message. Now I want to set it to data rate 5. And I need an activity. to receive the data. So the sensor is still in data rate 0 when I received the message. So it should be updated the next event. Okay, so here we have the activity during data rate 5. As you can see, the peak is much shorter. In data rate 5 we have a peak of roughly 50 milliseconds, and in data rate 0 we had 1.3 seconds. So let's measure the energy for this activity. So now the energy for the activity is roughly 2.4 microwatt hour per activity. So also here the sleep current is a factor of 1000 lower, so I disregard this during this measurement. So we need to calculate the energy here, and because we're going to have 4 of these short messages and compare that to 1 of these longer messages. So what need to be thought about is that when you work with optimizing your LoRa design, it's not always better to have higher data rate, because if you have too high data rate you will have a lot of need to resend information because the information was not being received. So that means a lot of transmissions, retransmissions, and this in the end might result in a higher current consumption than if you go to a lower data rate. So you need to try this out, adjust the data rate according to how well the message is being received. Another thing that is interesting is also in this case we got an average in the peak of just below 40 milliamp. So how is that affected by a lower voltage? Because the battery will drop in voltage. So now I have set the voltage to 2.5 volt instead of 3 volt. This is the part where I lowered the voltage, so I got a current rush. So let's have an event. So as you can see now, the voltage is much higher, 46.2 milliamp. Before it was 38 milliamp. So this sensor will consume more and more current the lower the battery voltage will go. This is also important to measure all the behaviors of your device. So what is important during the first step when you measure your device, you understand it, is that while you do your development, hardware and software development, measure all the time, because the changes you will do will affect the power consumption. So do modifications, measure. It's very important to measure all the time. Another thing, the environment will also affect your current consumption. So if your sensor is located outdoors, you will have a lower temperature, then this might also affect the current consumption of your device. So measure the current consumption for all environmental conditions that the device will be in. Another thing also is the placement. As you saw, if I had a lower data rate, the energy consumption increased. So if I'm far away from the gateway, I will force my sensor to go in a lower data rate, and that means that it will consume more energy for each transmission. So make sure that you measure all of these conditions as well. So all of this data, how the device behaves, will be used in the second step. And this is where we will profile the battery according to how the device will consume energy. Second step is to profile your battery. This step is regarding evaluating and choosing the right battery for your device. And as input to this step, we need the power profiles created in the first step. Possibly you already have chosen a battery. Otherwise, in this step, you will also profile several batteries and in the end evaluate the batteries and choose the right one for your use case. Let's begin with connecting the battery. So I disconnect my device. And I will profile a coin cell battery. So I connect the battery positive to the plus and battery negative to the minus. If I profile a battery that needs higher voltage than 3.75, then I need to again use the DC adapter. Then I can profile up to 4.55 volt. So for example, a lithium ion battery, I would need to have the adapter. But in my case, it's a coin cell, 3 volt, so I'm good without the DC adapter. Also, if I will profile a battery with a high discharge current, there is a risk that I get a voltage drop in the cables. In that case, I can use the sense plus and sense minus pins here and connect sense plus to the positive pole of the battery and the sense minus to the negative. And then OTI will compensate for the voltage drop in the cables. So let's start the OTI application, as I've done here. And now let's choose battery profiling. To use battery profiling, you need a battery toolbox, OTI battery toolbox, or the enterprise license. So here is how I set up the discharge. So I choose voltage, and that's the nominal voltage of the battery. This will be measured anyway, so it's more for information. And then I will choose a high current discharge and a low current discharge for the time high and the time low. And then I choose the exit condition where my discharge is ended, and that is by selecting my minimum open circuit voltage. So that's when the battery is not loaded, 0 milliamp discharge, or if I at any time reach my cutoff voltage. Or I can also choose to limit the number of iterations for my discharge. So the tool will then stop profiling when any of this exit condition is met. It will complete the already started cycle and then it will finish. Also, possibility to choose 4-wire for compensating voltage drop in my cables. And also I can choose to start a recording while I do the discharge. My recommendation is to not do a recording while you do discharge if you have a discharge that takes a long time. Then I can also add some battery details to remember what the battery model and manufacturer, etc. In our use case, in normal, you should be as accurate as possible. For this workshop, I will make a more generic profile, but actually when you work with profiling batteries, I suggest that you keep it as accurate and as much similar as possible as how your device consumes energy. But I will set it up with a simplified LoRa profile. I will keep it somewhere between data rate 0 and data rate 1. Data rate 0 has roughly 1.3 second high pulse, and data rate 1 roughly 0.6 second, as we saw in step 1. So I will choose 1 second high discharge. Actually, if I was going to do this, I would make one profile per data rate, because I need to see how the data rate affects the battery performance as well. So in this case, I intend to use a CR2450 coin cell. I don't need to connect sense plus, sense minus with this coin cell. The discharge is not that high. As I said, mainly interesting for high discharge like lithium-ion batteries. So I'll set the voltage to 3 volt. That's a nominal coin cell voltage. I will set the high discharge to 40 milliamp for 1 second. And then I will choose my low current to let's say 600 microamp, and for 179 seconds. And so how did I choose these values? I know that my CR2450 contains roughly 600 milliamp hours. So if I calculate this discharge, then it will take roughly 30 days. And that's a good time to discharge a coin cell battery. So depending on what I set as high and low current consumption and the timing, it takes different times to discharge. But this is, I believe, a good setting in this use case. I will stop my profiling at 2 volts. I will have a cutoff voltage of 0.6 volt. The reason for choosing this is that usually you don't discharge a battery, a coin cell battery, below 2 volt. And the cutoff voltage I set to 0.6 because I want to see the discharge as long as possible. I can also set the iteration. I don't want it to stop due to I reached the maximum number of iterations. I don't use a 4-wire. And normally I would not choose to automatically start the recording, but in this case I will do it, so you will see what it looks like. And then I have, it's a 02032 in this case, otherwise I would use 02450, and it's a no name. And it's this size, okay? Typically, this is very important setting, of course. The closer I can keep this high and low and the timing, the closer I can keep it as to how my device consumes energy, the more accurate my profile will be. But I cannot keep the same settings as my sensor here, because then I will probably be discharging this battery for 10 years, and I don't have that time. So I needed to do some accelerated discharge, and then all changes will of course introduce errors. So I need to do careful considerations where I increase the discharge. Okay, so we are ready to start the discharge. First it's calibrate the OT arc, and as you can see now it has started to discharge the battery. So here we have the 40 milliamp discharge for a second, and then it goes to 600 microamp for 179 seconds. So here we can see how the voltage changes during the discharge. And here you can also see where you are in the iteration of the discharge. So we are now iteration 1 is done, and it was when we had the high load. We are now executing iteration 2. Here we can also see the last measured voltage and how much energy that has been discharged from the battery. So we have one high discharge now every 3 minutes. So we just have to wait. And as you can see now, we have our second iteration after 3 minutes. You can also see that my voltage of the coin cell is above 3 volt, and that's normal with a new coin cell battery. So here we have a little bit above 3.2 volts. And we will see that the longer the discharge continues, the lower this voltage will be, of course, and the higher the internal resistance will be. You can also see that during this 40 milliamp pulse, you can see that the voltage drops drastically. So this will continue until we reach our exit condition. And then when that is done, the profiling stops, and you can then save your profile. So let's stop this for now. Then I can save it. Now it's not important to save because it's not very interesting profile here, but to show how it then looks like. So if I go to project settings, the profile is then saved, so you can find it here. So let me pick a coin cell. So what you will then see in the profile is the discharge curve for the battery. So the green curve is actually the open circuit voltage, and the red curve is when you discharge the battery with a higher current. So as you can see, I discharged this battery with 40 milliamp pulses for 1 second, but in the graph it says 50 milliamp, and the reason for this is that the OptiTool tool, it picks a good voltage curve. So it calculates this curve based on the discharge data that were being saved in the profile. Because what the tool does, it will profile the open circuit voltage, the internal resistance, and the used capacity for the complete discharge cycle. Okay, so this is the end of step 2. What is important during this step is to profile your battery as close as possible to how your device will use energy. Also, profile the battery in all the environmental condition your device will be in. If it's intended to be outdoors, you must make a profile in cold climate. If it's going to be in hot, high temperatures, then you also need to profile it in these higher temperatures. So all the environments that you intend to use your device, you need to also make a battery profile. You need to accelerate the discharge in most cases, because otherwise the profile will take too long time. So you may need to make careful choices how to accelerate the discharge to make the profile as accurate as possible. And when you do long profiling, don't start a recording, as this might slow the computer down. So for safety, I never record my long discharge, because the profile will be saved anyway. Okay, so in the next step, step 3, we will use these profiles that we have created in step 2. Okay, in this third step, it is to emulate the battery for your application. In this step, it is regarding letting OptiArc emulate the battery that you profiled in step 2. Let's start by connecting our device again. So I disconnect the battery and connect my sensor. So let's go to new project, and in the project setting here as supply, I then choose the battery profile that I have just created. In my case, I will choose CR2450R from Murata, and this is profiled according to the setting we just talked about. It's 40 milliamp high load and during 1 second. So this is the discharge profile for this battery. So I can decide where I want to be on the discharge curve for the battery. I can choose if I want to stay constant in a position, or if I want to move along the discharge curve as my sensor use energy. In my case, I would like to have it in track because I would like to emulate the battery, and the capacity will then increase. The use capacity will then increase as I use energy. I also need to enable the voltage channel and the current channel, because I would like to see both the current consumption and the voltage, because the voltage will show me voltage drop from the battery. Okay, so let's turn on. We should have a brand new battery. So let's power up. And again, I need to include my sensor in the network. I will set the height of this window so it's easier to see the voltage. So now I'm included in the network, but I need to change the data rate to data rate 0. And I will do that by sending messages to it. And since I have just included it in the network, I'm limited in how much I can send. So let's see if we are ready. So I force it to listen by an activity. Now we are in data rate 0. We see that now we are up to 1.3 second again. So this is data rate 0. So I stop the recording. So I rename this. So this is the include and data rate 0. So now I need to wait a little bit since I'm limited in how much data I can send. Okay, so I set this to 0 in use capacity because I would like to use it as a new battery. I will hide this and start a new recording. So this is my active event for when the battery is new. So I have my 38 milliamp, and during the transmission the battery voltage dropped to just below 3 volt. So this was the Murata battery at 0 milliamp hours used capacity. So now let's increase that. I'll increase it to 100 milliamp hours used capacity. And I wait a little bit, and now I start a new recording and I create my event. Okay, so this means that I was not allowed to send the data, so we have to wait until the data is sent. As you can see now, the battery voltage is much lower now when I have used 100 milliamp hours from the battery. There's my event. So I stop the recording. So this was 100 milliamp hours, but I would like to compare them, so I mark the area in between. And I'll move the yellow to the left. So now I can compare the two different used capacity. So now with 100 milliamp hours used capacity, I drop to 2.68 volt during my transmission. And as you see, my current consumption for this active phase also increases due to that the voltage drops. So let's continue increasing. So this was 200 milliamp hours. Now move it to the right. So now I'm down to 2.55 volt. And I will continue increasing until I reach my cutoff voltage and where I get my sensor to stop functioning. So this was 300. So now we're down to 2.31 volt. So I will try with 400 now. As you can see now, getting close to the end of this battery. Let's see if my sensor can manage this. Okay, we have to wait a little bit before. Yes, we survived. So this was 400. Oh, now we're down to 1.76 volt here. So I guess that we are really close to the cutoff. So I make just a small step now. Have to wait. Oh no! We failed here. So let's put it back to new battery again. Okay, so this was 410. And we failed here. As you can see, this peak is when we try to start a transmission, but then the voltage drops so much, so we cannot continue. So if I read in the Murata datasheet, it states nominal capacity is 500 milliamp hours. When I profile it according to my LoRa profile, I could get 444 milliamp hours until I reached my exit conditions. And when I emulate the battery with my sensor, then I could see that I could actually use somewhere between 400 and 410 milliamp hours. So that is my usable energy, and this is what we will use when we calculate battery lifetime. Okay, so let's try another battery that we also have profiled. So let's pick CR2450 from Energizer. And we start with a new battery. And create an event. So this was Energizer 0 milliamp hours. And let's increase to 100. As you can see, something will happen here, so let's be careful here. Okay. So I move a little bit slower here, 150. Have to wait. So now we are at 2.11 volt. So it's dropping pretty quick. So let's go to 200. Now we are in the slope here. So let's see what that means. Oh no! It couldn't handle that. Let's go back to a new battery again. Okay. So this Energizer 200 milliamp hour, we got a fail. So what is important here is that I have only profiled one battery for each manufacturer. So it could be that this battery that I profiled maybe was not the best battery in the batch. Maybe it was a bad battery. Or it is how the battery from the manufacturer, how it works. We are not sure. And to be sure, you must profile a lot. So you must profile several batteries in the same use case from the same manufacturer to see that you don't only do a profile for a bad battery, but that what you profile actually is what you can expect from this battery. That is very important. So in this case, I could not use 200 milliamp hours. So the truth lies somewhere between 150 and 200 milliamp hours for this battery. And now we have come to the point where we want to calculate the battery lifetime. So I have here my recording from the sensitive MHH sensor. So we have the two use cases. The use case 1 was with data rate 0, and I have that here. And we said that we wanted 1 transmission per hour in data rate 0. And the second use case was with data rate 5, and we have that here, and 4 activities per hour. So let's start with case 1. So let's zoom in. So this is our activity. So one activity, it costs roughly 44 microwatt hours, and we have the voltage 3 volt here. So if I divide it by 3, I get 14.7 microamp hours roughly. So I go from power to current. Not really, since it's hours as well. So this is the cost for one activity. And since I have one activity per hour, that means that I get, in average, 14.7 microamp current consumption for this activity. And I have disregarded the sleep current in this calculation because the sleep current is a factor 1,000 lower. But now, for this hour, I have this activity, and then the rest of the time I will be sleeping. So I need to measure my, here I have a longer period of sleep. So I have 1.44 microamp in sleep current. So let's say 1.4 microamp in sleep. So in total, if I add one activity and sleep for 1 hour, I get 14.7 microamp plus 1.4 microamp, and that's 16.1 microamp. And when we emulated the battery, we saw that Murata CR2450R, I could measure that I could use somewhere between 400 and 410 milliamp hours. So let's calculate for 410 milliamp hours. So then we take our 410 milliamp hours, that's our usable energy, and we divide it with our current consumption, average current consumption, and we said that was 16.1 microamp for 1 hour. So that gives us a battery lifetime of 25,500 hours roughly, and that is 2.9 years. So our first case with data rate 0, once an hour, with our Murata CR2450R battery, we estimate 2.9 years battery lifetime. Let's check our second use case with data rate 5. So the energy, the cost of sending, the cost of one activity in data rate 5 is roughly 2.4 microwatt hour. And again, we divide that with the voltage, 3 volt. So that means roughly 0.8 microamp hour per activity. And we will have 4 activities per hour. So we multiply it by 4. That gives us 3.2 microamp in average current consumption for these 4 activities. So again, we add that to the sleep current, and that was 1.4 microamp. That gives us in total 4.6 microamp. So again, we take our 410 milliamp hours and divide it with 4.6 microamp. And that gives us a battery lifetime of roughly 10 years. So our use case with one transmission in data rate 0, 1 transmission per hour, gave us battery lifetime 2.9 years. And 4 transmission in data rate 5 gave the battery lifetime roughly 10 years. Okay, I have a note here about this calculation, and what is not included in this calculation is the battery self-discharge. So I have done all the calculations without one really important aspect, and that is the battery self-discharge. So when you do your calculation, you have to add this yourself. So for example, it depends on the battery chemistry and the size of the battery, etc., how much self-discharge you have. For example, a primary lithium metal battery, like the coin cell I have here, they have a self-discharge of roughly 10% in 5 years. While if you have an alkaline battery, it's about 2 to 3% per year. A lithium-ion battery, 5% the first 24 hours, and then 1 to 2% per month. And if you have a safety circuit, which I hope you have, then you need to add on roughly 3% to this. And also, the temperature affects the self-discharge a lot. So a rule of thumb is that self-discharge, it doubles every 10 degrees Celsius. So if you intend to have your sensor in high temperature environment, then the self-discharge will increase a lot. And again, I cannot state this enough. All these calculations and profiling of the batteries is done with only one battery. So you need to give yourself more statistical background of how the batteries behave, so you can do an accurate calculation. Of course, you also need to profile the battery and profile your sensor in all the environment all environment and all use cases that it might be in. So if it's outdoor sensor, you need both warm and cold climate. You need to profile both close to the gateway and far away from the gateway. You need to try out different timing between transmission and sleeping, because the more often you do your transmission, the quicker you will discharge the battery, of course. So you need to take all of this into consideration while you optimize your device battery lifetime. So that's it from me. Thank you very much for your attention. I hope you have learned a lot how you can work with this 3-step method to optimize your design, working with the batteries, choosing the right battery, and then emulate the battery to, in the end, calculate the battery lifetime of your device. So thank you very much.